Okay, so let us now turn our attention to dynamic instruction scheduling techniques. And in contrast to static instruction scheduling techniques, we will now look at the opportunities we would have to design pipelines that actually resolve all the dependencies, structural hazards, control hazards as we are executing the program. So the problem with static pipelines, I would say the static pipelines can only exploit the parallelism exposed by the compiler. Okay, so instructions are stalled in the instruction decode stage until they are hazard-free, and then they are scheduled for execution. The compiler strives to limit the number of stalls in the instruction decode stage, but the compiler is limited in what it can do because, for example, it doesn't have access to it doesn't have any knowledge about the input data at the time we're compiling the code, and it also has a limited scope in terms of the number of basic blocks it can analyze. And what we really potentially would like to do is that to uncover instruction level parallelism, or ILP for short, across hundreds of instructions. Because the key goal is actually to find as many independent instructions as possible to keep a pipeline busy. For that we would have to cross a large number of basic blocks, in fact tens of branches. And what really matters fundamentally is the data flow, all of the dependencies between instructions. And it boils down to actually looking for respecting read after write dependencies. As we will see, all other dependencies can be dealt with, either with more resources or as structural hazards, or when it comes to write after read and write after write dependencies, we can deal with them, as we will see. So in dynamic instruction scheduling, what we do is that we decode instructions and then dispatch them in queues while they wait to be scheduled until input operands are available. So there will be no stall at the decode for data hazards, okay? Only structural hazards. So as long as there are available execution resources, then we can dispatch an instruction for execution. To extract and exploit a vast amount of ILP, we must meet several challenges, okay? So first of all, we have to deal with all the data hazards, read after write, write after write, and write after read. They are now all possible, and it doesn't only concern register dependencies but also memory dependencies, and they must be avoided. For example, if you have two memory instructions, one store followed by a load, and the store modifies data at the same address as the load will load from, then of course the data that was written must be reflected when by the subsequent load instruction. So these things we have to take care of. And we have to execute beyond conditional branches. We cannot afford to stall, so that will lead to what is called speculative execution, which will be a topic that I will deal with in the subsequent lecture in detail. And on top of that, we will have to enforce the precise exception model. As we said, there are in standards, for example, for floating point operations, that those assume a precise exception model, so we will have to deal with that as well. So there are lots of challenges, but we will take them one by one and see how we can build a very effective pipeline that doesn't only rely on the compiler's ability to schedule code efficiently. So let's start with an example. Here we have again a pretty similar loop what we have looked at before, but we don't do any code scheduling. So we have the two loads, and then followed by an add, and then followed by a store, and then some management code to increment the memory registers and the loop index variable. So now let's execute that on a standard pipeline as we have seen, and let's zoom in on when we have launched the add instruction for execution in the floating point pipeline. Then the problem is that the store will sit in the ID stage to wait until the add instruction has finished, because it needs the output operand before it can launch. The problem with that is that although all subsequent instructions, which are integer instructions, could actually bypass the store and get executed through the integer execution execution stage, they are blocked because of the stalled store instruction. So first of all, the add immediate could obviously launch as soon as the store instruction has read from R1, because otherwise we would create a write after read hazard, of course. So that could move on. The same goes for the second add. There is no problem with that, so we could also let that go. And the same goes with the subtraction instruction. That will not create any hazards. We could also let that bypass the store. And the same goes actually with the branch instruction as well. And the whole problem is related to the fact that the store instruction will block in the ID stage. So that one we would like to get rid of. Now the problem with the pipeline so far is that it actually sequentialize all instructions through the ID stage, right, where we read from the operands. We would like to go beyond that limitation, so we're now going to look at a redesigned pipeline to allow more concurrency between instructions. But before we do that, let's look at a quiz. So we have this loop we have seen many times, okay, and the question is how fast we could execute this loop if we didn't have this limitation with the ID stage, okay? So we just respect ideally the dependencies that are there, the hazard, read after write, write after read, etc. hazards, and how fast could it be executed. Now let's look at the code. So there are these read after write dependencies between the loads and the add, and between the add and the store. So the least number of cycles we could ever get this done is gonna be 9, okay? But if we allowed the subsequent integer instructions to really continue to bypass the floating point instructions, then they would get done in 5 cycles. So that is in the same amount of time as the store instruction gets done. So in fact we could get done exactly at the point when the store instruction is done. So if we add the cycles, it will become 9 cycles. So alternative A and B are not correct. Now let's move to dynamic instruction scheduling, and a very important technique which is kind of challenging to understand, and it's known as Tomasulo's algorithm. It actually is an old technique, but is still doing well. It was first introduced by a person whose name is Tomasulo in an IBM machine in the 60s, and has been incorporated in pretty much in its spirit as it was in the earlier IBM machines in today's microprocessors. So we first redesigned the pipeline, so it's worth spending some time on getting familiar with this new pipeline diagram. So it consists of two parts, the front end and the back end. And front end is essentially what we have seen to the left in our pipeline so far, the instruction fetch stage, okay? And the back end is actually where the execution stage is, and what we're also going to see, where we read the operands and things like that is going on. All right. So at the top of the pipeline diagram, we have the instruction fetch stage. And here we simply fetch instructions from the iCache, and they will get dispatched. They are decoded also, and then they are immediately dispatched to one of many execution units, okay, depending on the type. So in this particular example, there is an integer execution unit, memory operation execution unit, and a floating point execution unit. But you could think about any other kind of setups here. It's a very general kind of structure, layout. So in the integer execution unit, we take care of what we did in the execute stage, adds and branches and those kind of instructions. But we have a special queue for execution pipeline for memory instructions, and apart from what is new here is also that we have added a load and a store queue, which then interface to a data cache, okay, and I'm going to talk more about that in a few minutes. And then we have the floating point unit. Again, nothing more to say about that at this point. But now really how instructions are dealt with in this pipeline differs significantly from what we have seen before, so we better look in detail what happens in all these stages, and by following an instruction from the front end to the back end, okay? Before that, actually, there is of course the register file, and a very important concept called the CDB, or control data bus. To say something about that is that when an execution unit completes its execution, then the output operand will be put on the control data bus to be transferred to any other execution unit, for example the integer unit, for those instructions that are waiting, have a read after write dependency on that instruction. So that will be fed to that, and also written back to the memory, and we're going to specifically look at the support to make that happen. So now let's look in detail into what happens when an instruction flows from the instruction fetch stage all the way through the pipeline. So first of all, instructions are fetched and stored in the FIFO queue called instruction fetch queue. So basically the front end works, asynchronously with the rest of the pipeline, to just with the only sole task of fetching instructions, okay? And when an instruction reaches the top, it is decoded, and a type of instruction will dictate which execution unit it should be dispatched to, okay? So with each execution unit there is an issue queue for and the instruction will simply be dispatched to that. So in contrast to the pipelines we have seen before, in the decode stage we don't read from the operands, okay? We don't read from the register file. That's very important to note. We just dispatch it as soon as we can, and of course if all the instruction queues are filled up, or the specific queue that this instruction needs is filled up, there will be a structural hazard, so it will sit and wait in the instruction fetch queue until it can be dispatched. Moving down to the back end, so let's assume that we have an integer instruction. Now it will be sit in the integer issue queue. So instructions in issue queues wait for their input register operands. So here it's the time to read from the registers, you could say. But you can only read from the registers if that operand is not under execution, is being produced. If there is a read after write dependency, then it will actually sit and wait until the result is available. Okay, and that turns me to and when that is available, it will be dispatched for execution, and when the result is ready, it will be put on the control data bus, and it will be possible for other instructions that are waiting for this operand to read it, and when that happens, those instructions get ready for execution. Okay, so that is what is going on here. So note also that since all instructions have access to this control data bus, there could be multiple instructions waiting for the same output operand, and since it's a bus, all those instruction issue queues will get access to the value in the same cycle. Now, how does Tomasulo's algorithm resolve hazards? And this is in a very interesting way. So when an instruction is ready to be executed, it has all its input operands, then it will be the output register will be assigned a tag, okay, in the register file, and the tag is actually linking it to the execution unit, or the instruction issue queue, where the instruction that is producing that output register is executing. Okay, and the tag will be reclaimed when the instruction writes its value back to that particular register. And when an instruction finishes its execution, it will post the value plus the tag, so that all instructions that are waiting for exactly this tag for this operand, we have a strict read after write dependency, we see, oh, now that value is available, so they will grab it from the control data bus. Okay. This is an so this will first of all deal with read after write dependencies, but what is so interesting is also that it will deal with write after read and write after write dependencies as well, because if there is a subsequent instruction that will write to exactly the same architected register, that will receive a different tag, okay, than the tag used by the previous instruction that is reading from it. So even if an instruction after that is issued later will write to the same register as previously executed one is waiting for, they will be associated with different tags. So we basically do, you could say, dynamic register renaming through actually assigning different tags. So all types of hazards are possible. So this is a general solution to really dealing dynamically with the three types of data hazards that are possible. Read after write, write after read, and write after write. Now, moving to memory operations, there is also possibility for data hazards, of course. So we could have store followed by a load to the same address. And the way to deal with this is actually to store all pending. So first of all, we have an address generation unit that computes the address. You can see it's pointed to, it's called AGU, okay? And then secondly, we have load store queues. So all loads are buffered in the load queue, all stores are buffered in the store queue. And if there is a store followed by a load to the same address, then that will be detected in this memory disambiguation unit to really make sure that the load is returning what the store is writing to memory. Now, as far as structural hazards, will simply be if the queue is full, then if an issue queue is full, then dispatch must stall if all entries in the issue queue or load store queue are occupied. And the instructions cannot be issued in case of conflicts for the control data bus or functional units. As far as control hazards, dispatcher stalls when it reaches a branch. So branches are dispatched to integer issue queue as integer instructions, and they wait for their register operands and put outcome on the control data bus. And this is very important, because if we would issue instructions from the dispatch queue, then we could actually change the content of the register file before we have validated the outcome of the branch instruction. Okay. So if untaken, then dispatch resumes, and it has actually done the right thing. It will just continue to dispatch the next instruction on the following instruction memory addresses. And if it's taken, then the dispatch clears the instruction fetch queue and directs ifetch to fetch the target instruction stream. Precise exceptions, they are not supported in this case, so we will deal with that actually later. So now it's time for the final quiz for this lecture. Which of the following statements are incorrect? And I encourage you to stop the video now and think about these different statements before I reveal the correct answers. Okay, first statement is Tomasulo resolves structural hazards by not issuing any instruction to a queue until an empty slot in the queue is available. That's absolutely correct. So for example, the instruction fetch queue will not issue any instructions until there is an available slot in the specific instruction issue queue that is needed for the particular instruction. B. Tomasulo resolves write after read hazards by forcing instructions to read from the register file in program order. That is not correct, because Tomasulo allows instructions to read from the register file out of order, or actually read operands out of order, and it does that by associating a tag instead of a register to the destination operand, as is correctly stated under C. So now let's take a more global view of what Tomasulo actually does. So write after write and write after read dependencies, they are also called false or name dependencies in the literature. And read after write dependencies are called true dependencies. False and name dependencies are due to limited memory resources. Okay, so in the Tomasulo algorithm, we solve read after write and write after write hazards by assigning result output operands a tag, the issue queue number. So now let's look at a sequence of instructions here. there are some important observations here. I3 may complete its execution before I1 if I1 misses and I3 hits in cache, but I2 waits on the tag if I1 of I1 and not on F0 or on the tag of I3. This is very important. So actually what Tomasulo manages to do is to avoid the write after read hazard between I2 and I3. The tag of F0 in the register file is set to I1's tag when I1 is dispatched, and then to I3's tag when I3 is dispatched. And even if I3 completes before I1, the final value of F0 is I3's. So thus the write after write hazard between I1 and I3 is also avoided. Finally, the value of F0 produced by I1 is never stored in register. It is a fleeting value only consumed by I2. And the important thing here is, of course, that the final value to be reflected in F0 is the one produced by I3 and not by I1. So here is an example. Tomasulo. We have an integer instruction of 1 cycle and a floating point instruction of 5 cycles. Okay. So each entry is clock cycle number, and the task is to fill the table clock by clock. So instructions are issued and start execution out of process order. That's what Tomasulo allows us to do, right? There's a large overhead to manage instructions, so latency of operation is effectively increased. The structural hazards, both concerning CDB and function units conflicts, could take advantage of static scheduling, and branch acts as a barrier to parallelism. So now the major takeaway from this lecture is the following. We have reviewed statically scheduled pipelines, how out of order completion can allow a lower CPI. We have looked at static instruction scheduling techniques, those that work on the basic block level and are constrained by that. And there were a few opportunities, but fairly limited such. So we also looked at global techniques like loop unrolling and software pipelining, with the aim of actually creating larger chunks of code to allow more flexibility in code motion to get rid of stalls associated with hazards. We also looked at super pipeline and superscalar static pipelines and exception handling in those pipelines. Then we moved to dynamically scheduled pipelines, and a very important concept taught today is Tomasulo's algorithms. Tomasulo algorithm, its pipeline structure, and especially how it avoids read after write, write after read, and write after write register memory hazards. Thank you.